Right. So what is it in extended Kalman filter, which was not there in the standard Kalman filter, right? Now, when Kalman presented his celebrated Kalman filter, right, and there was one guy in the audience, right, in that conference, he was actually battered with this same problem. How do I deal with sensor noise? How can I know the state variables, right, emits the sensor noise? And this was like a directed pathway for him. He was from actually NASA. He was working with the space programs, so how to bring satellites and space vehicles onto the target. Okay, so he has to deal with he had to deal with the sensor noise all the time. So then he, after the conference, he actually he got this standard Kalman filter, but one of the problems he found there was the filter is a linear filter. Okay, state space model is linear. You can see it over here, Kalman filter. Look at this equation. This is a linear model. It works on the linear models. Whereas this guy from NASA, I forgot his name, he was dealing with nonlinear plans, right? Spacecrafts, a bit complicated than the linear models. So what he did was he used the Kalman filter, standard one, and developed what is called the extended Kalman filter. He extended the standard Kalman filter to what he called extended Kalman filter. The extension here is actually now the extended Kalman filter can use nonlinear plants, which means any plant. Okay, right. So this is a very brief introduction to EKF. I think the best way to understand EKF in the context of the standard Kalman filter is to put the equations side by side, and then you can immediately see what is new here. Now, the first equation of the Kalman filter, standard one, is the posterior priori estimate of the state at k plus 1. What is the state at k plus 1, right? The prediction, and that is this equation. You're coming from previous xk, your best estimate, right, and your control signal at that moment, okay, and you predict. This is like dead reckoning, okay. So it's a linear prediction. Whereas in the extended Kalman filter, it is a nonlinear function. We don't know what it is. We can't write it like this shape. Nonlinear plants we write like f of x, u, and all the other things. Even time can be a part of that. Any function. When you don't know what the function is, this is how we write it. Just a function, okay, of these arguments. And also the second equation, priori covariance prediction, right? Your estimation process is not perfect. It has an error covariance. There's an error plus or minus, but average error is 0, but there's a variance, right? So this is that variance. In Kalman filter, it is minimized. And that equation is also a little bit different, right? So there you can see the f1 here, the function, right, is the partial derivatives, right, of the function, this one, with respect to the state variables. So this is actually rate of change of the function here with respect to the state variables. Okay. Now, this is very much in line with what we already know. Now, if you know your position and if you know your velocity, in fact, this is kind of velocity, you can predict your future by multiplying the rate of change, this one, with time. Okay, again, dead reckoning. So all the other equations are same. Kalman gain calculation, state update, posteriori state prediction, and the covariance update. Same equations, right? The only thing is now you can use a nonlinear plot, nonlinear model, the Kalman filter. Okay. So if you want to use a extended Kalman filter, you got to have these elements. you need to have f, right? G, H, Q, R, and P plus 0, X0, U0. This is the initial values of the control input state and the sum estimate of the error covariance. Okay, so with that, you can actually run an extended Kalman filter. So let me show one of these examples.
So they are in the slides. What's the notation that dot means in the letters in previous slide?
Dot is actually what you need to get going. If you see all these dots, okay, they are here.
All right.
Right. So if you know these things, dots, then you are ready to go. Now, look at this example. A nonlinear system xk plus 1 is linearized at a point, right? Say k. Now, this is the equations given to you, right? Your xk plus 1, by the way, x is a vector here. It has a number of states, x1, x2, and so on. In fact, in this case, two states, x1 and x2, okay? It's a column vector. Given by this, right, x1k, and then the second row is x1k, x2k, right? So now if you look at this process, right, beyond what you see in mathematical equation, the x1 goes from k to k plus 1 to k plus 2, and it's not going to change. It remains. Look at that. x1k is equal to x1 k plus 1. So it's not going to change. But if you look at the other one, that is x2 k plus 1 is equal to x1 k, this one constant value actually, times x2k, right? So it is going to change. The second state variable is changing in a bit complicated manner. Okay. So we write these two equations, right? f1x, f2x, because this simple f is actually this f. Is a general function, okay, not a linear separable model like this. Because now you have x1 and x2 multiplying each other, okay? You don't have this x1, x2 multiplying in a linear model, okay? Right. So we can just write this as a function of x at k plus 1. Now, we know that fxk, right, the state at k, right, and also the rate of change at k. If you know these two, you can actually predict your values at k plus 1. This is the Taylor expansion, isn't it? Right? This is x0, this is x1 times the rate of change, the time difference from 0 and 1. Then you get your value at 1. Okay, I mean, if I say k equals 0 when you get going. So this is very typical in controls in math, in engineering, right? You predict your future state using your present state and the rate of change, right? It's a very common formula, Taylor's formula, very old equation. Now, because you know f, right? This is your f. You can differentiate this f with respect to x1 and then with respect to x2. Okay, so you get the first row and the second row. Take the first row first, which is just x1k. Differentiate with respect to x1, you get 1. And then differentiate with respect to x2. This is independent of x2, so it is 0. That is the first row. And the second row is this one, differentiate with respect to x1. So the answer is x2. And then differentiate with respect to x2, the answer is x1, which comes over here. So this is the Jacobian, that is the first order partial derivatives of x, of f rather. Okay, so this is what you use in extended Kalman filter, rate of change. So using this one, you can get going. Any k, you know the value, and this is the rate of change. You multiply this rate of change with the time difference and add that to the plant. Okay, so you can get going. And there are other things given to x10 is 0.9 and x20 is 1.2. And by the way, as you see over here, x1 is not going to change because x1k plus 1 is equal to x1k. And then it's going to be equal to k plus 2, k plus 3. It's not going to change. And the value is 0.9. It's going to stay at 0.9. But x2 is going to change, right? From 0 uh, times 0, it is 1.2. And if you look at over here, time 1, it will be 0.9 times 1.2, and it goes like that. So gradually decaying, starting from 1.2, because every step, it is multiplied by x1k, which is 0.9. So this is like a series of equations, right? A series of numbers. It is a compound series, right? Every step you multiply by 0.9, 0.9, 0.9, right? Keep going, and you see an exponential decay, right? And there are other things given, process disturbance and also sensor noise, they're all given, right? Then we can actually do this in MATLAB. So I have my MATLAB over here. You can see the code, right? So that is the code, extended Kalman filter. I implement these 420 steps, and this is my function. You can see this is not a linear state space model, right? It is x1, first row, x1 and x1 times x2 is the second row, right? This is the process. And H is this is the drive matrix, right? Measurement, sorry, this is not the drive matrix, this is the measurement matrix, right? The output of the plant. And we only take x2, right? We don't worry about x1. Here, the variable of interest is x2, right? So I have these two functions here to represent my model, my process. So this is the XP predicted state, right? At k equals 1, all of the states, right? And XC corrected state, right? At k equals 1, right? These are initial correction, initial prediction and initial correction. Because to get going, you need something initially, and you have to assume if you don't know some of these uh, variables. And this is the PC corrected error covariance, and initially we give it like identity matrix 2 by 2. And this is the process noise. You get the RMS of the process and then generate the covariance matrix. And sensor noise is like that. And this is the initial condition of the state 0.9 and 1.2, as I explained. And over here, what you have is you run the system without noise from k equals 1 to capital N, entire sequence, right? Using the two functions given, f and h. F is the process, h is the measurement. So your measurement, you put it into y, okay? And your state, you put it into x. So you have a graph from here. You can plot a graph of y um, versus time, because you generate y over here. Y is actually, as you know, it is x2 coming from here, second state variable. Then over here, number 2, we have the response with the process disturbance. So what we do here is that the same thing we had earlier, but you can see over here, it is not just the function, but you have the noise added. So we have the process noise uh, times the random signal. So it's a random signal, okay? But we know how much the RMS value is of that signal. So we have specified Q earlier, and you put it over here. Okay, and then you have your output measurement with sensor noise. The process noise and sensor noise, they both added. You have that there. Then you have the Kalman filter going on over here, which takes the capital F, right? This is the partial, uh, this is Jacobian, right? Jacobian. You use this one to predict the future state using the nonlinear model. Okay, using nonlinear model, you predict the future states. And these are the Kalman filter equations basically. Okay, and then down here you have YC, the corrected estimate, and also the error covariance in the process. And then you plot it. So let's see the graphs. So this is it. Right, there you can see, as I explained, we have two states and we only measure the second state, and we start it with 1.2 somewhere here, and it is actually reducing the value and is being multiplied by 0.9, right, starting from 1.2. So every step the value is multiplied by 0.9, right? So the value of x2 is only 90% of the previous value. It goes like that. So pretty obvious, right? So this is the shape of the actual state. But the thing is, now there's a process noise and there's a sensor noise. So therefore, with noise, you can see the pink line here with both noise, right? Actual signal is something like this, right? It is a very, very ugly signal. You can see it goes up and down. And if you feed this signal back to the controller, right? Controller will confuse and controller will respond to that, and your result will not be good, right? Definitely. So that is why you need to get rid of this sensor noise, right? But keep the process noise intact. Okay. Now, if you look at the blue line here, this is the state with the disturbance, because the disturbance is something we need to consider. So if you look at the blue one, right, that is with the disturbance. That is with the disturbance, right? And then we have extend Kalman filter in black, which produces something closer to the blue line, right? Kalman filter, extend Kalman filter is supposed to track the blue line. If you can see the blue line and the black one, you can see there's some, they're not identical, of course, right? But it is much better than using the pink signal. Okay, right. So there are limitations of the extended Kalman filter, also depending on the degree of non-linearity, right? This might not work. There are limitations. So that is why you need to simulate it in MATLAB extensively and then use it in practical applications. But certainly it will enhance the performance, right? Even though it is not perfect, it will enhance the performance significantly. All right. Any questions about the result here? Right. Now, if you use the extend Kalman filter, there are ways to do that. Like I have coded over here. That is one way. But if you do a complicated system where you have the MATLAB code and also a Simulink block, you have a MATLAB extend Kalman filter block. You can use that block and fit it to the uh, uh, fit into your MATLAB, Simulink file, just like over here. This is the Kalman filter block. Same as this, there is extended Kalman filter block. You can bring that and put it over here. And when you go into that block, it is a different block than this one. This is a linear block, A, B, C, D. You have to input A, B, C, and D. When you open, double click on the block, it asks you to fill the form, right? With A, B, C, D, etc. But when you go to the extended Kalman filter block, when you open it up, it asks you to fill it. Okay, what is this nonlinear function? What is the Jacobian? Okay, what is the external signal coming in, right? You have to know the template. Okay, it's like form filling, right? You have to write your name, your birthday, your address in respective places, like that. Kalman extend Kalman filter asks you to fill those things. Okay, once you do that, it will work. Okay, any questions, please? That's the last slide and the end of the Kalman filter lecture.